Hi everyone, so Mrs. Valdivia here. We're going to be going over chapter 8, our chapter on energy, which is the study of thermodynamics. Right, so let's write that down right here. Thermodynamics. And thermodynamic is literally just the study of energy and temperature changes. So if we take a look at this sample image that we have here, we have snow. It's a very cold day, but you also have a combustion reaction occurring. So we have different forms of chemical reactions that are happening. Energy is changing, it's going from one system to another. And the study of all these chemical changes through energy changes is known as thermochemistry. So we have two different definitions. So the first one, thermodynamics, the study of energy and temperature changes. So study of energy and temperature changes. And then the next one is thermochemistry, which is part of thermodynamics. So it's like a subsection of it. Thermochemistry. Thermochemistry. About to write thermodynamics all over again. So thermochemistry. Energy changes in chemical reactions. So energy changes in chemical reactions. All right, so let's look at all the different chemical reactions in this picture. Because of this combustion reaction that's occurring right here, we have heat being released from the wood out to the surroundings, right? And it's boiling a pot, like a stovetop right there. And that pot has food that he's going to consume, right? So all of that is going to be a whole bunch of chemical energy being put into his body, right? And it's going to produce energy inside of him. So that food has potential energy. He's going to consume it, chemical energy to give him energy, right? Then because of the heat, the snow is starting to melt. And what it's doing, it's absorbing, taking in a lot of energy. To absorb, right, is to take in. It's taking in energy and it's starting to move a lot faster, right? Because when you take in energy, like if you drink an energy drink or anything like that, you start talking a lot faster, you start moving a lot faster, you start doing things, right? And that creates a lot of kinetic energy, which is energy in motion. So that leads us to our two forms of energy. We have potential energy and kinetic energy. So let's go ahead and write those ones down as well. So potential energy and we have kinetic energy. Those are our two forms of energy, potential and kinetic. And when we start writing these, I'm just going to write PE for potential energy, and I'm going to write KE for kinetic energy. And potential energy is stored energy, and kinetic energy is energy in motion. All right. And energy is just defined as the ability to do work or to create changes, right? So both of these are forms of energy. Energy, right? And I said the definition of energy is defined as the ability to do work or bring about change, in other words. So bring a change in the system. Bring a change in the system. So be able to do some work. So that brings us to two types of energy changes. The two types of energy changes are going to be heat and they're going to be work. So two types of energy changes. How it changes. Right? So how does energy change? Energy changes via heat and work. Heat, which is the transfer of kinetic energy. Oh, I was going to write K and I totally forgot. So heat is the transfer of kinetic energy. And work is the transfer of energy. Um, yeah, it's just the transfer of energy from one form to another. One form to another. All right. Now, when we look at heat, okay, the transfer of kinetic energy, if you have an increase in kinetic energy due to absorbing energy, then what you're going to have is faster movements. Faster movements, right? And then the opposite is going to happen as well. So heat is the transfer of your kinetic energy. Work is the transfer of energy from one form to another, whether it's kinetic to chemical or anything like that. All right. So the way that I want you guys to look at energy is look at energy as the transfer of wealth, right? Someone had money, he was very, very hungry, so he bought himself some food. In this case, he bought himself energy. He gave energy to get energy, right? So he spent money, but in return, he received a product, and that product satisfied his hunger, and he was able to obtain energy to withstand the rest of the day. For us, money and energy are going to be simultaneously used. Okay, so energy is the unit of energy is going to be joules, and that's going to be the wealth in chemical reactions. And that wealth is going to be we're going to be looking at it through heat and through work. Now, through all wealth goes through the law of conservation of energy. Basically, energy cannot be created nor destroyed, so that's something to remember, right? We can't create it, we can't destroy it, but we could transfer it, just like we transferred that money. And when we look at transfer of work, right, from one form to another, think about money again. Okay, we could have a physical dollar bill and we transfer it to the bank. We go to the bank and we deposit it into a bank, right? And then we could use an app on our phone to simply transfer energy from our checking into our savings without physically touching the money. So now we've turned physical money into electronic money. And that's kind of like work, right? Transferring from one form into another. Now, the units of energy that we're going to be looking at are going to be joules, BTUs, kilowatts, calories, right? But they're all vary depending on what you are talking about. So if you have a heater, for example, a heater is going to use a British thermal unit, a BTU, and because one BTU is equal to like 1,055 joules. So it's easier to just say one BTU, kind of like when we have the mole, right? One mole is equal to 6.02 times 10 to the 23rd atoms. Well, it's easier to say I have one mole, right? Um, so same thing here. Instead of saying I have 1,055 joules, I'm going to say I have one British BTU. So one BTU. Um, the kilowatt per hour is used for electronic substances. So with an electronic substance, kilowatt per hour is equal to 3.6 times 10 to the 6 joules. Now, do you really want to say that? Or do you just want to say I have 1 kilowatt, right? 1 kilowatt is a lot better. Now let's look at a calorie, not the food calorie. The food calorie is the capital C calorie. This calorie right here is just a unit of energy, right? And sometimes we do talk about it as a nutritional calorie. That's the only way we look at it. But a calorie is also used for like water, heating of water, boiling water, those kind of things. And 1 calorie, lowercase calorie, is equal to 4.184 joules. And that's important because those are the units that we're going to be using a lot, right there. So because I said it, let's write it down. 1 lowercase calorie is equal to 4.184 joules. Okay, and 1,000 lowercase calories is equal to 1 kilocalorie, which is equal to 1 capital C nutritional calorie. So those are like little things for us to think about and look at when it comes to the calories. And just note that this is right here a nutritional calorie. All right. Okay, so let's go ahead and talk about this example. Its example is going to be a piston like the pistons that we see in a car. And in a piston in a car, what it does is it uses the gasoline, right? The gasoline, and it heats up the gasoline, creating a combustion reaction. The combustion reaction produces energy. That energy pushes up onto the piston, okay? And it helps our engines go. Well, when that reaction happens, right, the expanding gas does work pushing up onto the piston. So as it pushes it up and it physically moves it, it is doing work on the piston. Now you're going to notice though that not all pistons, when you touch them, they can be kind of hot, right? So we don't touch a car, the engine of a car right after we use it because it's going to be hot. And that is because some of the energy escapes in the form of heat, right? So energy gets released, you have work being done, and you have heat being released, okay? So the equation that we use for that one is the change in energy is equal to the heat plus the work, right? So this is a very important equation that we're going to write down because we will be using it. The changes energy is equal to the heat plus the work. Now, depending on the type of work and depending on the type of heat that you're going to be using, these values could either be positive or they could be negative in values. The delta E stands for change in energy. So this is going to be change in energy. The Q is going to be our heat. And the W is going to be our work. Okay. All right, now let's look at this one. Okay. If the piston is sealed, so therefore it's not going to move no matter how much pressure you're going to put, then no work is going to be done on this piston. However, you had energy that was being produced through that combustion reaction. And what's going to happen is that energy is still going to escape. So therefore, in this reaction, all of it is just going to be heat being released in the form of energy. Okay. Now let's go ahead and look at this small question right here. All right, so in this question, what we're going to see is a small sample of propane, and it's going to burn in a combustion reaction. All combustion reactions produce carbon dioxide and water vapor. And as that happens, the water vapor and the carbon dioxide gas, well, they expand because gas naturally expands, right? And it's going to be a very hot mixture because it's a combustion reaction, right? It's fire being produced. So it's saying it's releasing 20 kilojoules of heat and does 31 kilojoules of work pushing up against a piston. What is the total amount of energy released in this reaction? So let's go ahead and look at this. Energy released is Q plus W. We have 20 kilojoules of heat being released and 31 kilojoules of work pushing up on the piston. Therefore, the energy being released is 51 kilojoules. Now, I want you guys to note that it says energy released on here, right? That's extremely important. Don't just say energy, because we have not introduced the changes, the positive or negative changes, depending if work is being done on a system or if work is being done on surroundings, which we're about to do. So in this example, very important to write energy released. Okay. All right. Let's go on to the next part. And we're going to be talking about what is exothermic and an endothermic reaction in changes. An exothermic reaction, which is what we just saw in the other problem, is a release of energy that is produced in a chemical reaction. It's produced, right? That's an exothermic change. It releases energy. In an endo to enter, exo is to exit, endo is to enter. Energy is being absorbed. It's entering the system. So it is part of your reactant. So energy plus solid water or solid ice, in this case it's ice, is going to produce liquid water. Okay, and that's because it absorbed energy and increased the kinetic energy inside of it. All right. So work can be done on the system and it can be done on the surroundings. It can be done on both of these. The system is the part of the universe being studied, and the surrounding is the rest of the universe. Okay. In one case, we have the piston doing the combustion reaction doing work on the piston, and the other case we have the surroundings doing work on this piece of ice, right? So exothermic reaction, endothermic reaction, and you know what? Let's go ahead and write down exothermic and endothermic reactions and what they both are. So exothermic reaction, exo is to exit, right? So I'm just going to write exit here so we could remember that, is to release energy. And an endothermic reaction, endo right here, is to absorb energy. Okay. Now, what we're introducing now is something called a system and a surrounding. A system is like our piston. That's what we are studying. What we are studying. Are we studying the piston? Are we studying a chemical reaction inside a test tube? That's the system. The surrounding is what is surrounding our system. It's the rest of the universe. So we're going to call it the rest of the universe. Okay? And that's literally going to be what is surrounding our system. So what surrounds our system? Okay. A good example of this is going to be an ice pack on a swollen ankle, right? The ice is absorbing heat, right? Because you know the ice packs don't stay icy for that long, right? They get really soft. And that's because it absorbs heat from the ankle, right? So in that case, it is an endothermic reaction occurring to the ice pack. Yet the foot is releasing heat. It's releasing the heat towards the ice pack, right? So the foot is encountering a exothermic reaction. Okay. And it's also doing work on the system and surroundings in itself. So the foot is releasing heat to the ice pack and to the surroundings also, okay, to all of it. All right. Now, let's go ahead and this is a very important chart that we're going to write down. So I'm just going to put it all out here so we could write it down. And this is the showing directions and changes. So remember I said we're going to be adding values, positive values, negative values, all that great stuff, depending on what it is that we have. So if you have an exothermic reaction, you're releasing heat, you're going to have a negative Q value. So this is going to be a negative Q value. So negative heat because heat is being released. Release energy or heat, right? So that's going to be a negative Q value. When you have an endothermic reaction, you're absorbing energy or you're absorbing heat, and that's going to be a positive Q value because you're absorbing heat. Now, when work is being done on a system or work is being done on a surrounding. So if your system does work on the surroundings, then you're going to have a negative work unit, okay? So you're releasing energy, so it's going to be a negative W. If you're absorbing the energy, you're going to have a positive W. And those ones, it's actually probably better to write those down. So let's write those down right here. If the system does work on surroundings, so system does work on surroundings. So like the piston releasing energy, okay? If the system is doing work on surroundings, it's going to have a negative W value. It's releasing energy. So this is to release energy. But if the surrounding does work on the system, then we're going to have a positive W. And that's because it's going to be absorbing energy. All right. We did mention earlier the law of conservation of energy. It's similar to the law of conservation of matter. Energy cannot be created nor destroyed. It can only be transferred from one form to another. So let's go ahead and write that down. The change of energy to a system is going to equal the negative change in energy to your surroundings. That means you cannot lose energy, right? It's going to go somewhere. Something's going to happen to that energy value. Um, this example right here is a monopoly example. So it's basically saying that the money you start off with is all the money that's available in the bank and whatnot. It's going to be the same amount of money that you end with, right? At the end of the game. Okay. Not all the players are going to end up with the same amount of money or anything like that. But at the end, the board will still have the same amount of money. Okay. All right. Let's look at this reaction. A chemical reaction releases 200 joules of heat energy to its surroundings. So it's releasing. What does releasing mean? Okay, if we're looking at releasing, we're going to have a negative Q. It's releasing it to its surroundings. So it does work to surroundings, negative W. Write the change of energy for the system, the chemical reaction, and the surroundings. Well, the system, the change in energy is equal to negative 200 joules, right? Because it's releasing energy in the form of heat. And the surroundings, well, the surroundings are absorbing that energy now. So the surrounding is absorbing energy, and it's going to have a positive 200 joules in this reaction. Okay, so that's like a one way of looking at it right here. Our system, negative 200 joules because it lost energy, and our surroundings is a positive 200 joules because it gained the energy that the system lost. A way of looking at that one is if we have a container, right, like the piston, and we're saying that the piston just released 200 joules. So there was 200 joules here, and it released it. And the 200 joules are now out here. So this is losing it, and the surroundings is gaining those 200 joules, right? So summarizing, energy changes, work is work and heat. We have systems and we have surroundings. Our reactions could be exothermic or endothermic, so therefore we could release heat or we could absorb heat. And the energy is not created nor destroyed in any chemical reaction. Okay. This next section is going to be 8.2, and I'm going to make another little PowerPoint for 8.2. Ciao.